So, welcome everybody to our webinar, Block Domain Crossing. My name is Eugen Krasin. I'm your presenter today. You can actually look at our training calendar, which is actually shows you, all the trainings we are offering. Okay, now let's actually start the presentation. What is the block domain crossing stuff? Okay, so that's actually the agenda. What I'm going to talk about is the metastability overview, synchronizer, MTBF, and 3 flip-flop synchronizer, synchronize the fast signal in the slow clock domains, and then different solutions, open loop solution, closed loop solution to do the synchronization. Some simple, but yeah, we need to talk about how to pass multiple signals between your domains instead of single signals, multi-cycle pass formulation, and closed loop multi-cycle pass formulation. So these are the typical solutions we can use for the CDC. So overview. So this means this is actually the part. Can I do this? Okay. So this is actually, if you look to the FPGA design flow, the CDC and the solution for this, and actually the designing of CDC structures, it happens actually right here. Okay, so because you are responsible for this during the design engine. This cannot be done, automatically by the synthesis or by the physical implementation, whatever. No, you have to do it. We have to do it. The problem with CDC is the CDC is can almost not be found by simulation. So this means you have if you do have a CDC problem, okay, we will talk about what is a CDC problem. But if you have a CDC problem, it's almost impossible for you to find the CDC problem by running a simulation. No, it's not possible. This means you need another method. How can we understand, oh, I do have a CDC problem? And the point is, we do have that. It's very good. It happened actually a few years ago, a few years back. What we got a very, very nice tool inside the Vivado environment right here. This is a CDC checker. This means a CDC checker will tell you, you do have a problem here, and now we do have to analyze the problem and to find the proper solution for this. That's actually the idea of where we are in our general FPGA design flow. So we have to put it right here. This is not really possible for us for the CDC problem, so this means we need to run the CDC checker actually during the design flow. Okay, so that's the general idea. So now, what is the metastability? Now let me do maybe just to show you. Check here. Let me check here. I go right here to my notepad, and let me actually show you what is the problem. What is the problem with the CDC metastability? Okay, let's look at the flip-flop. So this is a flip-flop right here. Okay, so we do have a clock, and we do have a data and input and output. Let's say the data here. So if you look to the data sheet of this flip-flop, what is the vendor of this flip-flop? What is he saying? He tells you, well, this is the clock. Here we go. But the data must be available to the flip-flop maybe in this area. This means I don't care here, but the data input must be in reference to the rising edge of the clock. Here we go. You have to make sure a setup time is maintained here, and of course you have to make sure a hold time is available here. Okay, if this is true, then well, the flip-flop will actually behaves as indicated. This means it is good. It would look like this. You have here the time axis. You have here maybe the clock at time point 0. Here we go. That might be the output Q here. And that might be the low value, that might be the high value. Here we go. And then let's assume flip-flop is set to 0, and then we just apply the clock edge, and we make sure the timing for the data input is correct. Then of course the flip-flop output will change. Here we go, from 0 to 1, which is completely correct. That's what we expect. Very nice. But the point is, we cannot assure that this situation is always present. No, what may happen if also something like this, you have an FPGA right here. Okay? Maybe you have a clock generator right here, and we just go to the FPGA, and then maybe we do have an external source of a signal, and this is basically connected to a flip-flop inside the FPGA. Here we go. But this signal is completely asynchronous to the clock. This means we cannot trust, we cannot expect that we do have this situation. We cannot expect it. So this means we will violate the input. So this means now what happened? What happened if you violate the input? The vendor of the flip-flop tells you, oh, don't do this, don't do this. I don't know what will happen, what happens. Of course you know what happens. And this is the model, what we can have, what we can think of by figure out what happens with output Q if you violate the input. So the model is very simple. We just take a piece of paper, whatever, we just build a hill. And then they have a tennis ball right here, or maybe right here. Okay, now, and this is the model. So this is a mechanical model of flip-flop. This means if tennis ball is at this position, so this is maybe low, and if tennis ball is at this position, it might be high. Now, how can you transfer this flip-flop model from low to high? Yeah, we just basically take the ball, invest some energy, and throw the ball right here up the hill. The ball will climb up to the hill and finally goes down. So it means now we just move the flip-flop from 0 to 1. And this is actually what happened here. This means this area here is nothing else. And the energy we do have to invest in the flip-flop in order to move from this position to this position. We have to spend energy to climbing up the hill. So this now you know what will happen if we violate our situation, our timing input. So then if we violate this area here, so we invest less energy. So less energy, this means the ball will climb up and then go back. He'll climb up and then go back again. This means if you violate this, then the output of flip-flop will be something like this. It will climb up and then it goes back. And this may happen, of course, in several situations. So that's the expected output, okay, of the flip-flop. Even it can stay a little bit and then go up or go down. The problem is, that's the biggest problem here, that at the next rising edge, if a flip-flop is here, then this flip-flop, which is actually reads in this input, we'll see at this edge here, we'll see this value of this signal in a forbidden area. This is a metastable value, and that's my problem. That's exactly my problem. Okay, this means we have to avoid. We cannot avoid this situation. We cannot avoid the flip-flop will behave like this, but we can avoid the propagation of this error. So that's all about. That's our problem of the metastability. This means if I just look to my presentation again, so that's actually here. That's what I draw. That's actually the model of our flip-flop. You see, if you meet the timing, that's okay. Or the output out will, if there's the input, then the output will follow. That's okay. But if you here maintain the setup and hold time, it's also okay here. But you see here, if we just violate this setup, or the whole, then you don't know what will really happen here. What will really happen here? It may go up, or it may have some ringing, but then still go down. So that's a big problem. So this means, what should the flip-flop which is connected here next? What should this flip-flop do? A big problem. So we need to avoid this. This means this is one very, very important rule. If you do have a flip-flop which runs with clock A, and we do have a flip-flop which actually runs with clock B, so different, they are completely different, they are not synchronous, okay? Then this flip-flop, you cannot avoid this. This flip-flop will start ringing something. It's a certain probability, but it will. So this means the output here will do something like very, very strange stuff. You don't know. So this means now you have to take care. What about the following component, which is actually connected? So this flip-flop usually always has a name. It's called the sync. This is the sync flip-flop, okay? So this is the sync flip-flop here. Here we go. So this means, how can we do this? And the point is, this ringing, this metastability happens whenever you violate the input and the setup time and the whole time. When this is a violation, then you will get this ring. And this is a certain probability to do this. So this means that's a very, very big problem. The first rule, never take this signal from the sync flip-flop, okay, and then use it at a different location. Never do this, because of this ringing, okay. This signal may be interpreted somewhere else as a 1. The same signal at the same time. Maybe you connect here, a flip-flop here and a flip-flop here and a flip-flop here, okay. So then this flip-flop may take a 1. This flip-flop may take a 0, and this flip-flop again may take again 1. So that's a problem. The same signal will be interpreted completely different, and this means your FPGA will not work. That's a big point. Now the question is, how can I actually correct this error? And now we do have a synchronizer. Okay, it's called the synchronizer. But before synchronize, we're talking about this, the synchronizer. We do have two situations. Okay, sometimes it's permitted to miss samples. You don't have to. If you pass signal from one domain to another, it's permitted to miss samples. For example, you're just sampling status information, so you don't. In sometimes every signal which is passed should be taken. So there are two different kind of situation. It's permitted to miss it, okay, or it's not. So depending on this situation, we can have two or more, not two, just two, more different types of how should I perform the synchronization. That's maybe the very, very simple one. Maybe that's what you are using all the time. It's called the two flip-flop synchronizer. So this means this is clock A. Here we go. And this is the synchronizer consisting of two flip-flops. This means you use a logic. Now you can split it here. Yeah, now you have the fan out here. Okay, so this means now we have here the clock A, maybe here. I don't know, maybe something like this. And the clock B is, and the signal clock A maybe gives the data. I don't know, maybe this way. Okay, and now your clock B. Now you do the violation. Maybe your clock B is somewhere here. Okay. So in this case, this flip-flop gets violated, but we don't care because this gets violated. It starts ringing, okay. But this ringing signal is followed by one flip-flop. So this means this flip-flop must now make the decision. Is it 0? Is it 1? So now the decision is made. We don't care. The decision 0 is correct or the decision 1 is correct. So we don't care about the value. But the point is, this flip-flop will make the decision. This means all this object which are follow this flip-flop will see a 1 or a 0. Okay, so that's the point. That's called the two flip-flop synchronizer. Okay, and now I've prepared a few examples just to show you what's going on. First, I just did a very, very simple example. I just used this one FPGA. Here we go. have an external signal called X clock, and maybe external component, which is actually you know, sending a signal called enable and to the FPGA, and then you have a 200 megahertz clock, which is a huge as this clock. So, and now I do something like this. It's obvious it will not work, because now this this signal is captured correctly here, but it's captured with the clock X clock. But this counter, it's a counter enable, must count with 200 megahertz. So in this definitely that must be an error. If you run a functional simulation, you will not see the error, because in a functional simulation there's no delay. Okay, so but if you run a timing simulation, then you will also not really see what happened here. Then in this case, this counter will actually run to X, but you don't really understand why it's X, because in this case X would be because of the violation. So that would be the timing constraints for this. I don't like to talk about timing constraints now, because it's I think the next part of my webinar. But the most important part is here. I say the two clocks. First, I define the clock, this clock and X clock, 200 meg, 100 meg, and then I say, hey, these two clocks are completely asynchronous. They are not synchronous, they are asynchronous. Okay, you don't know it, you don't know the phase relationship. And now, if you run this, okay, now let's actually look to the my example. So this is example one. You see, in the example one, if I just look to the FPGA, you see that's enabled, that's a Q out, that's X clock, and then you basically say, I just take the enable and capture this with the external clock, and I take the captured enable and use this as to count the counter, which is actually defined here. Okay, so if I do this, and let me run the synthesis, then you will actually see that we will get exactly the structure what we expect. Okay, so 1 second, it will takes a few seconds actually. So this means now I will actually see what is actually the synthesis results, okay, of this, and we will actually expect here, and then we run the analysis. And what we expect is actually, I would expect an error message from Vivado telling me, you have a problem here, you have a problem here. This flip-flop is talking to this device. Okay. But they are completely asynchronous, and you have a CDC problem here. Just go ahead and correct it. That's my expectation. Okay. Now let's still running here. It's not because it's a complex, not a complex device, but sometimes the synthesis is still a little bit slow. Here we go. Now I just open the synthesized design, and when we look to now I just actually go and look to the schematic. Okay, so now you see exactly really the schematic. So I just go. Here we go. So for the schematic, you see here, that's X clock, that's enable, and this is capturing of the first flip-flop. Now the signal, which is called enable 1, that's what was the name, enable 1. It's actually shown here, you see here. So it's actually, and this is the counter representation, it's driving the enable of the counter. But the counter is actually clocked with this clock. And this is actually completely wrong. How can I figure it out? Okay, I can just go tools, reports, timing, and I say, give me the information first, give me the information about the clock interaction. Show me what is the edge of my clocks. I do have two clocks. So if I ask for this, then the tool shows me, well, you do have an external clock and a sys clock. Now the connection. External clock is talking to external clock. So this is a green area. So it's okay. Yes, of course it's okay, because this is exactly this. The external clock is talking to external clock. This is exactly this part. Well, this is definitely okay. Okay, so therefore it's green. Now, there's no connection from sys clock to X clock. There's no because it's black, because there's no connection. But there's a connection from X clock to sys clock. There's definitely a connection. It's blue. And you see, it's this connection here. It's this exactly this connection from X clock to sys clock. It's this connection. Okay. And of course, there's also internal connection sys clock to sys clock. So this is shown here, because sys clock to sys clock is green. It's okay. Green means everything good. Blue means, oh, user ignored path. This means, hey, be careful. There's a path exists, but it's not really correct. You ignored it. Why? Because I said, here, timing constraints, I said, hey, these two clocks are completely asynchronous. Because they define this to be asynchronous, there are interpreters, oh, don't care. But it's not true. But so this means this block interaction will just show you, yeah, it could be a problem, but maybe not. Now I need to understand, is it really a problem or not? Now I'm asking for the CDC. I say, report timing, give me the CDC. And now, if I now I get a new window here and say, hey, you do have a problem. A connection from X clock to sys clock. Here we go. And it's completely, it's not safe. It's and that's critical. It's a problem. So if I look to more detail, it tells you, well, we don't have a connection from from flip-flop enable 1, this is called enable 1, to my counter. And I say, oh, what is it? You just do a click here or select here and right click and say, give me the schematic. Here you go. And then it shows you, yes. So this is the X clock, which capturing the enable and is driving the enable pin of the counter. But the counter is running with sys clock. This is a problem. And I don't know what you do, but this is definitely not correct. So now we know, okay, that's a problem. Okay, now let me close this again and the schematic. And now I'll say, okay, we understand this. Now, let's look at the second example. The second example, now I just added a register here, just one. And maybe somebody would expect now it's correct because we are synchronizing the signal here using enable 2 before we actually use this. No, it's not correct. But this is not a two-stage, it's a one-stage synchronization. So in this case, if I take the example 2, again, I go over here back again. If I take the example 2, which is right here, I just say now, I put everything in one project so I can select the top level. So in example 2, now example 2 is my top level. And if I look to this now, you see the example 2 actually takes the enable here, but then have a one clock, which is, you see, one clock and capturing the one stage. Okay, so if I do this again and I run the synthesis here, then, and again, let's look to the timing. Okay, just, well, the information is the same. Then we just, well, I can use the example timing concept from example 2 and example 1. They are the same. The only difference would be setting the false path. That's what you will see, what the difference is. But if I just running the synthesis, let's check then what we do expect. Now we would expect here that now the timing from here to here is correct. Yes, the timing would be correct. The timing would be correct. Here, this this connection from AN1 to AN2, this completely asynchronous. So therefore, to make it easier, we should maybe define a false path. Don't care about this because I will synchronize the signal. So that's the meaning of the false path. We'll talk about the false path in the next webinar. But anyway, because this is just one stage and not two stage, I do expect again a CDC error here, because the Vivado will tell me, oh no, one flip-flop is not enough for you to solve the CDC problem. So that's what I would actually expect. And you see here in my timing constraints, I set myself false path. Here we go. I said false path from AN1 to AN2. Here we go. And this is actually the false path. To make it easier, because it's anyway, it's asynchronous. There's no, there makes no sense to define any time because you don't know. So it's a false path. Okay. Now let's actually look to my Vivado. It's now we open the synthesized design again, and now we do expect actually one flip-flop before we actually connecting the counter. Now we just load the synthesis results, and we look to the schematic, and now you see now we do have here again, there's a capturing of the so that's a capturing of the first flip-flop, use the X clock. Now synchronization with the flip-flop runs with the sys clock, and now actually that's a connection of the counter. See, we do have one stage synthesizer here, and now let's actually again check the timing, the clock interaction. So for the clock interaction, there's no change because it's the same. We just defined the asynchronous and the false path between X clock and sys clock. The rest is okay. But now let's actually run the CDC. So if I run the CDC, then we will actually see that I get again a warning. Hey, you do have just 1 point, just because it's flip-flop to flip-flop. See, just 1 point. Yes, of course, it's just the point from here to here. It's 1 point. Okay. You do have a synchronization, but it's not safe. It's also not unsafe. I don't know. I don't understand what you're doing here because it's not really a correct CDC. So it's not okay. This means when I just look to the details and just look to the schematic, then he tells you, yeah, that's exactly this connection. X clock is driven here. Then you have a next flip-flop, which is actually okay. I can also show you here. If I click on and say say expand here, then you will actually expand to leaf. Okay, here we go. So then you see here that's a counter. So this means that's exactly here. That's the connection which is that's a problem. Okay, that's the clock. This clock, X clock, that's a problem. This will not work, and we'll get exactly this problem. Now let's do the next example. Say now let's make it correct. So in order to make it correct, now we do this. That's what I discussed already. And say, hey, let's do this for two-stage synchronization. So and now we have two stages here. Okay. So in this case, I just I will a little bit later talk about what this means, asynchronous. Now let's do this. Okay. That would be the correct situation. Now let's look what is Vivado telling you now. So in this case, we just go to Vivado here and say, okay, that's actually example 3. And again, run the synthesis. for this, and then we will actually analyze the results. So what I can tell you, it will run in the background, and then we will look at it. So what will happen now? Vivado will tell you, yeah, everything is okay, everything is okay, no CDC error. But Vivado will tell you, maybe you know already, maybe you know that this is a shift register. Okay, this is a shift register. Okay, which contains 2 flip-flops. So this is a 2-bit shift register. But there are 2 ways in the FPGAs, in the AMD FPGAs, to implement this register. It could be real flip-flops, or it could be RAMs, which are connected to the shift register. RAMs, they don't have any, they are not hardened to metastability, they are very bad. Flip-flops are very good for metastability issues. Therefore, if you just describe a shift register, then Vivado tells you, okay, it's good idea, but make sure this shift register is not implemented with RAMs. It must be implemented with flip-flops. And so in this case, you use an attribute, just point this attribute to this flip-flop versus, okay, like, hey, this is a asynchronous register. This is a flip-flop, not a RAM. So in this case, would be completely correct. And that's what you will see actually when it's actually there. This means now, let me check. Okay, here we go. So now I open this, and then we will look to the synthesis schematic. So that would be the schematic. Now you see that's actually the first flip-flop, and this is a 2-stage synchronizer, and this is actually the counter. Here we go, 2-stage synchronizer. Now, if I do the report and just the clock index is always the same, so it's enough for us to look to the CDC. Now the CDC tells you, yes, everything, now no error, warning, tells you it's okay. It's completely safe what you did, very good, but it's still missing, async is missing, because I didn't this. If I look to the XCC, you see you're still using the same XCC here, but actually I should use this. And you see, set the property async to the flip-flop, and then we'll also actually get a warn, get rid of this warning. But you see, completely safe, everything is good, everything is known, and it's just warning because we're missing the rank. So you see, that's how we actually do this situation. Okay, now, so that was just to show you that's how you actually check your design. This means, so two stages, okay. Now let's go to the 3 stage. Sometimes it's not enough to have a 2-stage, a 2-stage synchronizer. We need 3. Why? It has just something to do with the MTBF, mean time between failures. Because if you look at mean time between failures, so it's dependency of the it's a constant, technology constant, but you see that's the block B, so this is the capturing clock, and block A, this is the that's the asynchronous sourcing clock, and that's actually the calculation of mean time between failures. You try to have it as fast as big as possible. Okay, so this means for higher frequency sampling frequency and high frequency clock A and clock B, okay, then 2 might be not enough. Okay, so you need to have 3 in order to increase your MTBF. But this is also supported by the Vivado. This means you just define the clock A, you define the clock B, which I already did. Then you can ask for the MTBF. If this is not big enough, if I refer to our specification, okay, if this is not enough, the customer asks for more, security and safety, then you can actually add 3, and then you will get a new value. Okay. Also, this is also not good. Even you say I do have a 2-stage synchronizer should be okay. This, if you do this would be generate an error, because even you can say that's asynchronous, so I don't care. But the problem is you have a combinatorial logic here. Okay, you can get, because the combinatorial logic is always the candidate. Maybe they have a spike, something like this. Okay, so in these spikes here, you'll increase actually the asynchronous frequency here. This means your MTBF will go down. Okay, so this means if you do this, don't do this, because your router will tell you, this is wrong, unless you can keep it, but usually don't do this, and you just add, a flip-flop here, and then it will be correct. Okay, now synchronizing fast signals in the slow clock domain. So it's easy for us to synchronize slow changing signal in the fast clock domain. Simply just do the sample. But what happens if you have a fast to slow? Well, that's not a big thing. There's just one single rule we have to look. It's just, if this is the asynchronous sourcing frequency and this is a capture frequency, if this is just in this case twice as high, you see, or no, the clock A and clock B, so this means, you see, clock B is not fast enough, and this means you can miss your signal. So the obviously it is not correct. Even if you have something, something this for this, the same frequency here, then you can violate it here, and you can violate it actually here. So this means if this is your capture and this is your sourcing, you can have violation here, and violation here. So this means what you have to make sure that the asynchronous signal must be seen by your capturing clock, in this case clock B, for 3 edges. It's 1, 2, 3. If this is the called C edge requirement. If you make sure you do the C edge requirement, it will always work if you go from fast to slow. Okay, so this means sometimes it's not enough just to generate a pulse based on the sourcing frequency. No, you have maybe to stretch the signal. So it's just simply use a shift register for stretching the signal, or counter or something like this. Okay. Now let's talk about the closed and the open loop. So this is called the open loop solution. What does it mean, open loop? Open loop means we just set a flag here, maybe, and that's it. And then this flag, which is actually here, maybe something like this, is just synchronized here and appears here. But we never know, because we are sending this from here, we never know, is this flag synchronized correctly or no? We just have some kind of a broadcasting, but we don't know, does the synchronized signal appear here or not? So it's called the open loop. So we do have advantages and disadvantages. Advantages, it's the fastest way for us to transfer signal. It's the fastest way. The disadvantage, we don't know. Is it correct? We don't know if, for example, if you change the frequencies, then maybe we violate the 3 edge rules or something like this. So we never know, are we successful or not. So you see, it's advantage or disadvantage. Okay, so this means okay, this is just the alternative. Instead of providing pulses right here, what could be done? We could also just simply do a strobe here and the input. Whenever we do a strobe, we will get something like this. You see? Oops, sorry. So this means if we ever get a strobe, something like this. So this is because of the XOR. This makes it simply easy to provide the data. That's actually just, by the way, that's what I'm also using a lot, just to make it easier to generate a strobe, which is covered here again. Okay, this is nothing special. So, but it's also open loop solution. See, we just define a strobe here, and then we just synchronize this. But once we synchronize this, we just take and do an asynchronous clear here. So it looks like a closed loop, but it's not. It's just make it free for the next pulse. This is very nice, but it's limited. It has some disadvantage. It is the strobe. So this means the strobe if you do this, you have some requirements. This means the sorry. So the strobe, the time t between two strobes here must be greater than two clocks, two times period of b, because if first we have to process this up and then we can clear it, and then the next can. So when you know that this will never happen, you can do this. Usually, if this is a microcontroller signal generated, or if this is a signal generated by the microcontroller, so that's actually what they usually do. It could also be done something like this, or here. Closed loop. So now the closed loop solution. What is if you need really? If we need to be sure that we really get and synchronize the signal, because if I go back, so this, for example, also here, for example, we just apply the signal here, but this could be missed. But we cannot afford to miss the signal. Then we can do something like this. We just place a signal here. Now the signal is synchronized, and then this signal appears after synchronization. The signal appears here, and now we just go back, synchronize it back, and so after by the signal, the technology appears here. So this means we just fire, then we wait until we get the feedback, and then we do the next. So this is already the first simple synchronization with feedback. Advantage: very safe, because we make sure we do the synchronization before we do the next. Very safe. Disadvantage is a potential long delay, because we need to synchronize here. That means this is a minimum of 2 TB, and then again we need to synchronize here. This is a minimum of 2 TA. So that's a long delay, but it's the safety. You pay, but you pay, of course, with your performance. Or you can do something like this. This is also recommended. It was, I don't remember. It's already pretty old, actually. It's 10 years old. I saw this recommendation the first time. This was done by, 10 years back by Xilinx. So you just place the data here to a special time point. You just place the data. You don't care. You just place the data. Okay. Then you just place a strobe here. Say, just enable here, you just provide a 1. So you get a 1 here. This one will be synchronized. Okay, because it's synchronized, then this signal can be used as an enable for the data. Because this is much later. This event is much later. In reference to the placing the data. So this is always safe. It's always safe. But because we actually did the synchronization, we just take the signal and just we send acknowledge back. Send acknowledge back, because we send acknowledge back. This flag is already cleared. Here we go. It's cleared already, and is actually prepared for the next shot. So this was, I remember, 10 years back, was a recommendation in one application note by Xilinx to run a communication between two independent clock domains. Now, passing multiple signals. So just go back here. So in this case, what we discussed so far is always passing just one signal. This is one signal, not two, not three. This is just one signal, single bit. So that's easy. Single bit is easy. That's all the solution. But what's happened if we need to pass multiple signals? Not just one, just multiple signals. And so we need to have some strategies. They are not very difficult, easy, but you need to think about these strategies. And and the strategies, what you can do. You can do a consolidation. Well, that's actually combination of multiple bits in a one signal. Okay, yeah. Or we can do a multi-sided formulation. Okay. Okay. So that's first the consolidation. Consolidation means, oh, that's very simple example here. Assume we would like to transfer the information from clock A domain to clock B domain to control a counter. But this counter is a special counter, has a load signal and has an enable signal. And they must be in a certain relation to each other. Okay. And now we transfer the signal for the load. Here we go. And in parallel, the signal for enable. Now the problem. These two signals, load and enable, must have a relationship to each other, because otherwise the counter will never work. There must be a certain relationship. For example, first the enable, then the load, or something like this. Okay. But the problem is, because we're using a single bit domain, it will definitely, the load signal will definitely be synchronized here. And this will also be synchronized here, but not necessarily at the same time. For example, this load signal can be captured 1 femtosecond later here. So it will appear complete cycles later, because there's a delay associated with the net and here. So as even a very, very small skew on the signal will lead here to a error. So now, this case, you should do some precautions here. Just combine these two signals in one single signal and then split it to each other right here. Just first, this is the first one, this is the second one, and then you can do it. Okay. So this means it's a time demultiplexing, what you can do. Very simple example, but you need to think about this, because otherwise it will not work. Or we do a multi-cycle formulation in this case. You know what I did is something like this. I just used the clock A and I used the clock B, and I just I don't remember, I think it was 2-bit. I just used 2-bit here, and just transfer this, but you see here, and I used a single bit synchronization. But this is actually an error, because this is not a single bit, this is 2 bits. So, and you see, you really see, you know what happened? And I run Vivado on this. And Vivado, well, I never checked this with the latest version. Maybe now it works in the latest version. I didn't check this, but in the prior version, Vivado said it's okay, because Vivado did not understand this is a multi-bit. So in this case, it was be careful here. Whenever you have a multi here, a multi-bit here, you will not see this. So that's what I did just for the simulation. I just assigned some delay, some skew on the signal, some skew, and then it are 2 bits, and it was maybe 0 0 0 1 1 0, and I transferred 0 1, and then I transferred 1 0. So I'd expect then the decoding, maybe this one and maybe this one. Okay. But in order to check it, I just model some delays here. And what really happened, I got also, instead of 0 1 and 1 0, I got a 1 1 in between. So this means I got this one here. And this is wrong. So be careful. You cannot do this. Whenever you have a multi-bit, you have to do something. You have to maybe have a feedback, or maybe you have to use, if it's possible here, gray coding instead of binary coding, just to make sure always 1 bit is changing, then it will be correct again. So be careful here. Okay. So in the multi-cycle, there are again advantages and disadvantages. Advantage, of course, advantage is the sending clock domain simply don't care about any rules, 3H or 2H, whatever. Just send it and wait for the feedback. That's a definite advantage, and it's always very, very safe. So disadvantages. And the disadvantage, of course, it's maybe the slowest method to do the communication. between the clock domains, but it is the best in terms of security, safety, and security and safety. Okay, and this actually very. I think this is the best situation that you can have. But of course, you see, it's also some. You have to put some effort in it. So now let's assume we would like to transfer data from A to B. So this is the data, we like to transfer this data, and we like to get this data. So first action, we just place this data on the bus. Okay, now there you go. Now, we do it here, actually a circuit which actually takes, this pulse here and transfers because of the feedback here. I just saying the pulses. So, and this multi-cycle with feedback requires a very simple state machine. So this state machine actually says, okay, I would like to send, am I ready or not? So in this case, let's assume we are ready. Okay, so now we would like to send the data. So we place the data here and say we would like to send. Because we are ready, we got a pulse here, and then it's actually generated here. And now this is synchronized because it's the pulse is then decoded again, and it's used to take the data here. Also because we just take this data are loaded here. And this is 2 cycles later, or even could be 3 cycles later, the data captured here. Because we just captured the data, we just have the feedback. Now we synchronize again, and we say to the state machine, yes, I do have to acknowledge everything is okay. And because everything was okay, the state machine say, well, I'm ready again. And because I'm ready again, you can use the next, actually the next statement, the next pulse. Very safe, very good, but it takes sometimes, you have to, it's not a big deal, but you have to have a small, very small state machine, and you have to have some register here, okay? But again, it's the best way for you to do it. Okay, so now let me show here. Oops, sorry. And this actually, that's such a good in time. I never was so good in time. 2 minutes left. So that's actually it was very, I think it was fast. Yes, it not all the information what could be which are available were presented here because lack of time. I do have only 1 hour, but you can get more information. Just contact us. Also, if you interested in the project files, like the last time, also some people ask for the project files, we send the project files. So also the examples I did, I can send it to you. And that's actually the result. That's actually in my last slide here. This means just to tell you, if I go back, just you can scan. You can scan it here, and actually, in this case, you would have a direct link to all of our offering. Okay, so thank you very much for your attention. I hope I could answer you some questions here, and you find this information interesting and needful for your work. So the next webinar, in my next webinar, I'm going to talk about timing, which is very important, and then it will be followed by synthesis circuit design using VHDL. There are 2 parts, and then simulation, again 2 parts using VHDL. So these are the next few webinars in the line. Okay, so thank you very much for your attention and see you maybe next time, and goodbye.